So here we were studying about the optimum filter. So here we can say optimum filter is acquired because it is used as a best linear estimate of a desired signal from a measurement. So here if you see, when we are supposed to see optimum filter, at that time we can say we can use a filter that will process the signal which we will desire. So here we are using the filter that will have various purpose, that can extract signal from noise, to transform signal, to suppress noise, to separate two signals that are mixed. So we can say optimum filter is such filter which we can use for acquiring best estimate of the desired signal from a noisy measurement. So it is different from all classic filters like low pass, band pass, high pass. We can say it is different because optimal filter are optimum. They are designed based on optimization theory to minimize the mean square error between processed signal and the desired signal, and which will equivalently provide the best estimation of the desired signal from measured noisy signal. So here we can say when we are supposed to see optimum filter, at that time if that filter will provide the minimum probability of error, and the filter or integrator we can say that as an optimum filter which will give us minimum probability of error. So here if you see the diagram, generalized receiver for PCM, here you can see the receiver for the pulse code modulations which we have seen. So here when we are using the pulse code modulations, at that time we are giving here input as a S naught T, or we can say as a SI of T. We are giving that. At the time you will get the output we can take as V naught of T. So we can say that will be equal to S naught T plus N naught T. That is nothing but the noise as well as the signal which we are sending. So if we are giving the input S1 of T, output we will get S01 T plus N naught T. Therefore we can say here when we are giving the input to the filter, at that time you will get here at the receiver for the PCM you will get the output, that is V naught of T equal to S naught T plus N naught. So we can say no noise is present there. So output is entire receiver assembly would be S naught naught or S naught 1. But here we will get the presence of noise because here we are getting S naught 1 T plus N naught T. Here we will get the noise. So here the decision boundary we can use, and it will give us the average of S naught naught T and S naught 1. That is nothing but you will get S naught naught T plus S naught 1 T upon 2. So here when we are taking S naught naught T will greater than S naught 1, at that time we can say S naught of T is transmitted, because error will occur if a sampling rate, the noise N naught T is larger than 1 by 2 S naught naught T plus S naught T minus S naught 1 T. So we can say here you will get the error that will occur if the value of that noise N naught T is greater than equal to S naught T minus S naught 1 T by 2. So we can say here you will get the probability of error that is equal to 1 by 2 ERFC in bracket S naught T minus S naught 1 T upon 2 square root of 2 sigma 0. So here optimum filter is the filter which will optimizes the ratio and which will give us the optimization parameter which will only depend on the difference signal, not on the individual. So here you will get the optimization parameter gamma equal to S naught naught t minus S naught 1 t upon sigma 0. So here we can say that optimization parameter is depend only on the difference signal. It is not dependent on individual signal. So here when we are considering the given signal of binary values logic 1 and 0, we can find format of modulated digital signal may be there is always a relation between them. So here if we will get the probability of error calculations, we can find the noise that will pulls down the higher level appreciably, and it will pulls up or boost the lower level appreciably. So we can say here when we are using the optimum filter, we must keep in mind that both distorted levels should not cross each other. If the distance between two logic value is high, then probability of error of occurrence is low, and the difference between transmitted symbol and the difference between output symbol of the filter we will get as Pi of t equal to S1 t minus S naught t, and at the output you will get P naught of t equal to S naught 1 t minus S naught naught t. So we can say here if we are taking the transfer function of the optimum filter, you will get P naught of f equal to h of f Pi of f. Pi of f, P naught of are the Fourier transform of Pi of t and Pi of f. So if we are taking the inverse Fourier transform, you will get the sampled filter output difference, which we will get as P naught of t equal to integration minus infinite to infinite P naught of f e to the power j 2 pi f t dm. So here we can say when we are calculating the optimization parameter, that will depend on probability of error P naught square of t upon variance sigma naught square. So we can say the process with this equation with the help of Scott's inequality is to be taken. It will state that you will get the equality will hold if you will get x of f equal to k into y star of f. Here we are taking k as a constant. Y star of f is nothing that we are taking as a complex conjugate of y of f. So if you compare equation 3.23 and 3.24, you will get x of f equal to x of f equal to square root of gn of f into hn of f, and you will get y of f that will be equal to pi of f e to the power j 2 pi f t upon square root of jn of f. So we can say the optimization parameter will hold the maximum value when we are taking from equation 3.25, h of f equal to k into complex conjugate of pi of f upon gn of f into e to the power minus j 2 pi f t. So here when we are using the binary signal is transmitting, it will corrupted by the noise, and you will get the received signal that we are filtering and sampling at the end of sampling interval of durations t, and you will get the filter output that we are taking as a y of t. So we can say you will get the filter output at the optimum filter. After the using the decision making device, you will get y of t equal to s naught t plus n naught t. S naught t will be produced by S of t signal, and n naught t is nothing but we are taking as a wide Gaussian noise, additive wide Gaussian noise. So you can say here when noise is present, output signal should be closer to S naught 1 t than S naught 2 t, and if output y of t will closer to S naught 2 t than S naught 1 t, we can say S 2 t will be transmitted. So here when we are using the optimum filter, in order to find the error probability of the optimum filter, we can consider if we are transmitting, you can see here, If we are transmitting out of two signal S1 of t or S2 of t. If we are transmitting S2 of t, we can say N naught t be a positive and you will get S naught 1 t will be greater than S naught 2 t. And if we are saying N naught t is larger, we will get error will be made in the decision making and we will decide that will be in the favor of S naught 1 of t. So if error in detection will occur, you will get that neta value will be, you can see here what we are saying, error will occur when we are taking N naught t will be greater than equal to S naught, you will get here error will occur if N naught t will be greater than equal to S naught 1 t minus S naught 2 t upon 2. Here we are taking S naught and S1 symbol. But instead, if you take S1 of t and S2 of t, and we are sending the second signal S2 of t. So at that time we can say error in detection will occur if N naught t value will be greater than S naught 1 t minus S naught 2 t by 2. So we can say here N0 of t is the random variable and you will get its power spectral density. And we have seen how to calculate its probability density function. So if we are taking N naught t as a random variable, we can write its probability density functions PDF of N of t. And you will get that will be greater than S naught t minus S naught 2 t upon 2. So here you can say that will be greater than this probability and at that time it will detect when S2 of t will be transmitted. So here you will get its probability of error that we can take as PE equal to 1 by 2 ERC in bracket S naught 1 t minus S naught 2 t upon 2 square root of 2 sigma naught. So here we are transmitting second symbol. So we can say the optimum filter has to maximize the signal to noise ratio. So you will get here you are supposed to maximize S naught 1 t minus S naught 2 t upon sigma naught 0 in a such a way that you will get probability of error will be minimum. So you will get, because this you will get as probability E equal to P of E equal to 1 by 2 ERC into S naught 1 t minus S naught 2 t upon 2 square root of 2 sigma naught. So you can say you will get here optimum filter that can be used to maximize the ratio S naught 1 t minus S naught 2 t upon sigma naught in a such a way that you will get its probability of error minimum. When we are saying, when we are considering a signal of logic 1 and 0, we will get whatever the format of modulated digital signal may be there and it will always a relation between them. So you will get here the during probability of error calculations we will find noise pulls down the higher level appreciably. And you will get the difference between transmitted symbol and difference between output symbol of the filter. You will get Pi of t equal to S1 of t minus S naught of t and Po of t equal to S naught 1 of t minus S naught of t. So if you are calculated its covariance, you will get its variance sigma naught square equal to integration minus infinite to infinite G NO of F dF. So here we can say when we are using the optimum filter, you will get optimization parameter gamma max square equal to integration minus infinite to infinite modulus Pi of F square upon Gn of F into dF. Remaining we will see in the next class. Thank you.